Thank you. I apologize for the long title. So I want to express my gratitude for the opportunity to talk here, and also want to extend my thanks for the postdocs who've done a great job at inspiring me here. So it was great to talk right after Andrew because he set the stage wonderfully for what I'm going to talk about. And the problem I'm going to talk about today is one that appears a lot in practice and has to do with finding out how fast it is we can determine whether two objects are similar or have similar substructures. So the generic problem is determining how fast we can solve the following problem. So P, A are n by n matrices. This product here denotes the so-called Hadamard product. I'm going to explain in detail what that means. And we want to solve for P subject to the following constraints. This is the identity matrix. And P Hadamard P should be equal to P. Okay. So for those like you who like to hang on to a geometric picture, you should think of A and B as adjacency matrices for graphs. So these are graphs between n vertices. And I can draw one for a concrete picture. Vertex 1 connecting to vertex 2. Vertex 3. So the basic idea is the adjacency matrix, an entry ij being 1, indicates that there's an edge between vertex I and j, and an entry ij being 0 indicates that there's no edges between the vertices. Now, the Hadamard product is a product that a linear algebra student would infer after you taught him addition of matrices. You just multiply the entries entry-wise. Right? So if you teach matrix addition and you said, guess what matrix multiplication would be, he would guess that you multiply the entries. And then you would hit him on the hand saying, that's not what you should do. You should do matrix multiplication the way I imply here, which is doing correlation between rows and columns. Now, this problem is NP hard in the sense that, in some sense, which would be completely formalized, captures the essence of the problems that are hardest algorithmically to solve. So it's not uncommon to make some simplifying assumptions when we're solving this problem and then see what these simplifying assumption tells us about the original problem. Now, one of the most popular simplifying assumption is to do away with this so-called binary constraint. This is just saying that the entries of the matrix P should be zeros and 1. And surprisingly, if the number of 1s in A and the number of 1s in B are the same, this is a question about whether the eigenvalues of the adjacency matrix A and B are the same. So quite surprisingly, quite naturally, eigenvalues come up in the picture. And it's been a question whether one could use eigenvalues to solve the problem. So thanks to a result by Babai, Grigoriev, and Mount in 82, they showed that if the multiplicity of the eigenvalues is bounded by a constant, then the problem can be solved. The problem of isomorphism can be solved in polynomial time. Now, since the eigenvalues come up so naturally, in our thesis, we suggested to study what happened if we could somehow inflate the graphs to hypergraphs. So I'm going to describe formally what I mean by inflation scheme. So inflation scheme, you should think about the analogy as looking at parachutes that are on the ground, and you're trying to tell whether they have the same shape. So you might go by the brand or the color, but they might lead you to wrong conclusion. Why not just inflate the parachute and see what they look like? So for graphs, here's the picture you should have in mind. There are many ways of doing an inflation, and what an inflation should do is to map, so it maps a binary entry matrices to binary entry hypermatrices. But what's crucial is that the mapping should preserve isomorphism, so as to preserve isomorphism classes. Let me show an easy example, the one you would think about if you were playing with this. So let me draw again the graph I had before. Sorry? Oh, hypermatrix. This is a wonderful question. So a hypermatrix, you should think about it as a cuboid of numbers. So matrices, you think of a matrix as a rectangle of values 0s and 1. And a hypermatrix is a cuboid of numbers. So I'm going to describe some scheme that allows you to turn a matrix, a graph, into a hypergraph, sort of triangles. Instead of looking at edges, we're going to look at triangles. So let's actually look at a natural scheme for doing this. So suppose you started out with this graph. Vertex 1, vertex 2, vertex 3, vertex 4. So our scheme is going to be to add a supervertex star, let's call it S, and then create a triangle between every other edge. And let me do it this way. Excuse my artistry. And then whereas the original graph had edges, edge set, the original graph, so this was G, had edge set here, V1, V4, V2, V4, V2, V4. Allow me to skip the others for interest of time. The hypergraph H, which is now the collection of triangles, is going to have the edges, hyperedges, V1, V4, star, V2, V4, star, and allow me to skip the others. So the argument is that if you had two graphs that were isomorphic, your hypergraph would also be isomorphic. And the point is that to describe hypergraphs, it's convenient to use adjacency hypermatrices. And let me describe or show what the basic idea was. So for adjacency matrix, we started out like this. We started with the matrix A. That was indexed by the vertices, V1, all the way up to Vn. V1, all the way up to Vn. Right? And you fill up the entries you put here for Vi, Vj. This indicates whether there's an edge in between the two. For a hypermatrix, and here we're going to be looking at 3 uniform hypergraphs, what you think about is a cube. So let me do this. All right, so and now you have sort of 3 dimensions. So this is going to be labeled by V1 all the way up to Vn. Here, you're also going to have, let's say, V1 all the way up to Vn. And finally, to be completely, we need V1 here all the way up to Vn. And every point in the lattice is going to be determined by 3 index. And you put a value, you assign 1 to an entry if there's a triangle spanning the points, and 0 otherwise. Now, what's interesting about the graph setting is that there's a natural algebra of matrices that we've benefited from. It even suggests how to do things like spectral analysis. So what we are able to see is that it turns out there's a nice algebra, which was suggested by the studies of association schemes, which teaches us how to multiply hypermatrices. And let me at least write the multiplication if I can't have time to discuss the spectral decomposition. So for hypermatrices, we look at the following ternary product. And I will explain in a second what it does. So the ternary product is defined CMNP, AMKP, BMNK, CKNP. All right. So this is a ternary operator. which is defined on hypermatrices. And if you look at what's happening, what you're merely doing is correlating rows, column, and the tubes along the z direction. Now, the observation was that if you wanted to write these constraints for hypermatrices, you could. And it wasn't so clear what the spectral decomposition should look like. Let me at least write the constraint and suggest our result. So it turns out that if you wanted to perform a permutation on the rows for a matrix, it suffices to multiply by a permutation matrix. And the permutation matrix and multiplication is binary. For hypermatrices, you're not so lucky. Here's what the same equation would look like. So you had P transpose, you have P, let me write it this way, P transpose. Let me do this. So I have this guy. This guy. So I'm left with this one. Right, and now I need one last one. Sorry. Two, middle, and now I need the last. Yes. So it's P transpose squared. All right. So I should check what the transposes are doing. Let me explain what this is doing in a second. So I still have the constraint that it should be binary. So let me write it this way. It should be equal to P. And now I should have the constraint that this thing also is orthogonal. And here's how the orthogonality is expressed. So this now is a Kronecker delta P transpose squared PT. OK. So let me. Oh, right. So this line is saying to actually carry a permutation of the slices now. So you should think about our cube, let me draw the cube, as having slices. And what you want to do is effect a permutation of the slices. And if you want to effect the permutation of the slices, you actually need two permutation so-called hypermatrices. So the operation is ternary, it's not associative. So you need sort of here P and the transposes. And the transpose is a cyclic permutation of the indices of our hypermatrix. So what's happening is that if you put P in the middle, you put A in the middle, you're acting on.
If you have three, you can multiply them together. I think there's something missing.
So 3 can be multiplied. So this. So, and now I have, oh, sorry. Right, so this one is the first one. The second one is this guy. Right? And then you have the third guy, this one. Right? So the argument is that you need to do a permutation of these slices. You need to do the same permutation of the slices in this direction. And you need to do the permutation for the slices orthogonal to these three. And you want them to be binary entry. And most importantly, you want to ensure that if you had entered the Kronecker delta does not change. So this is still the Kronecker delta. All right. Now, these constraints are quite analogous to these one because we're saying do a permutation on the row, do the same permutation on the column, and I want the output to be B. So here, I should want the output to be, if I start this by B, I want this thing to be B, where everything is a hypermatrix. Now, the question was, here, eigenvalues are well defined. Can one come up with the spectral decomposition here? Yes? Yes, so this is the subgraph isomorphism problem. And so this is the sub-hypergraph isomorphism problem. And that you're doing a permutation of the row slices, column slices, and desk slices, such that when you select the hyperjet edges associated with B, you get B back. And the question is, can one come up with a way to relax these constraints and say something about the family of solution that it suggests? All right. So I won't have time to get into the nitty-gritty of the spectral theorem, but the observation is that indeed one can parameterize this family of hypermatrices, and they turn out to be hard to describe in general, and one could also suggest a definition for a spectral decomposition. So we can show that the spectral decomposition exists, however, it turns out to be very hard to compute, and the hope is to be able to compute them, have a better sense of how they work. Right. So how am I doing on time?
I think you're almost finished.
I see. So I think that's all I can say given the constraints.